Welcome, my friends. In this video, we'll be solving trigonometric equations with the aid of the Pythagorean identities. If you have forgotten what the Pythagorean identities are, I have them on the screen now. We have sine squared plus cosine squared is equal to 1. This can be algebraically manipulated to solve for either sine squared or cosine squared. I always remember that 1 minus either cosine squared or sine squared always gives you the other one. 1 minus cosine squared is equal to sine squared, and 1 minus sine squared is equal to cosine squared. And then we have two additional Pythagorean identities. 1 plus cotangent squared is equal to cosecant squared, and 1 plus tangent squared is equal to secant squared. I always remember that a tangent-related squared function, either cotangent or tangent, is a Pythagorean identity. 1 plus cotangent squared is cosecant squared, and 1 plus tangent squared is secant squared. These can be algebraically manipulated to solve for cotangent squared or tangent squared. Cotangent squared is equal to cosecant squared minus 1, and tangent squared is equal to secant squared minus 1. Let's take a look at some problems. In this problem, we are asked to find all solutions to the equation 2 times sine squared of x plus 3 times cosine of x is equal to 3 in one revolution of the circle, from 0 to 2 pi. Looking at our equation, we notice that we have sines and cosines, which is not going to be very helpful if we would like to solve for x. If we could either change sine to cosine or cosine to sine, that would be very helpful. Thankfully, we have a Pythagorean identity that allows us to change from sine to cosine. Specifically, sine squared of x is equal to 1 minus cosine squared of x. As I always say, 1 minus either cosine squared or sine squared always gives you the other one, so 1 minus cosine squared is equal to sine squared. We can replace sine squared in our problem with 1 minus cosine squared, but make sure you use parentheses. If we distribute the 2 to both terms, we will have 2 minus 2 times cosine squared plus 3 times cosine of x is equal to 3. Now I'm going to want to move everything to the left-hand side of the equation so that the right-hand side is equal to 0, so I can use the zero product property in coordination with factoring to solve for x. I know that if I eventually want to factor, I would like to have my squared term be positive rather than negative, so I'm going to multiply both sides of the equation by negative 1. On the left-hand side, I will get negative 2 plus 2 cosine squared of x minus 3 cosine of x. On the right-hand side, I will get negative 3. If I add 3 to both sides of the equation, I will get negative 2 plus 3 is equal to 1, and then everything else will be the same. 2 cosine squared of x minus 3 cosine of x is equal to 0. I can reorganize these terms so that they are in standard form. 2 cosine squared of x minus 3 cosine of x plus 1 is equal to 0. At this stage, I can factor. You can think of this kind of like 2x squared minus 3x plus 1 is equal to 0. If you'd like to, you can make a u substitution, like I did in the last video, but for me, I'm going to go right to factoring. I know that I need two values that add to my b term, which is negative 3, and multiply to a times c, which is 2 times 1, or just 2. The two numbers that add to negative 3 and multiply to 2 are negative 1 and negative 2. Negative 1 times negative 2 is equal to positive 2, and negative 1 minus 2 is equal to negative 3. The way that I factor when I have an a value multiplying my squared term that's greater than 1 is that I make the chart and then I divide each of my values on the left-hand right-hand side of the chart by the coefficient on my squared term. That means I must divide each value by 2, since my a term is 2. Then I should reduce if possible. Negative 2 over 2 is equal to negative 1 over 1. Now I always still write this as a fraction, so keep this as a denominator 1. From there, you can read from bottom to top. The bottom of your fraction relates to the variable, in this case, cosine of x. The top of your fraction relates to the constant, which is negative 1 in both cases. So the left-hand side of our chart gives us 2 cosine of x minus 1, and the right-hand side of our chart gives us cosine of x minus 1. By the zero product property, either 2 times cosine of x minus 1 is equal to 0, or cosine of x minus 1 is equal to 0. So we can individually solve each of those equations. If we add 1 to both sides in the first equation, we will get 2 times the cosine of x is equal to positive 1. If we divide both sides by 2, we will get that cosine of x is equal to 1/2. We need all the times when cosine of x is equal to 1/2 on one revolution of the circle. Cosine is equal to 1/2 twice on the unit circle, once in quadrant 1 and once in quadrant 4. In quadrant 1, cosine of pi over 3 is equal to 1/2. In quadrant 4, we have 5 pi over 3. So our two answers related to this equation are x equals pi over 3 and x equals 5 pi over 3. As for the second equation, we can add 1 to both sides. We'll get that cosine of x is equal to 1. Cosine of x is equal to 1 only one time on one revolution of the circle. Cosine of x is equal to 1 when x is equal to 0. Since they have indicated that we should include the value 0, but not 2 pi, our answer should be 0 rather than 2 pi. These are our three solutions. X is either equal to pi over 3, 5 pi over 3, or x equals 0. All three of these values satisfy this equation. Let's try another problem. We are asked to find all solutions to the equation sine of x plus 1 is equal to cosine of x in the interval of 0 to 2 pi on one revolution of the circle. Now the goal with solving all of these trigonometric equations is to first get everything in terms of the same trig function. In this case, we have both sine and cosine, so we would like to either convert the sine to a cosine or the cosine to a sine. Unfortunately, there is no identity that directly changes sine to the first power to cosine or cosine to the first power to sine. However, the Pythagorean identities relate to squared trig functions, so if we square both sides, then we will be dealing with squared trig functions, which will allow us to convert to other trig functions based on the Pythagorean identities. Now, you have to be careful whenever you square both sides of an equation, because you have the possibility of introducing extraneous solutions, which, in other words, are solutions that are not really solutions. The reason why is because there are actually two values that, when squared, can give you any particular value. For example, if I had negative cosine of x on the right-hand side of my equation and I squared it, I would get positive cosine squared of x. If I had positive cosine of x on the right-hand side of my equation, I would also get cosine squared of x. So there is no way for our function to differentiate between if we started with negative cosine or positive cosine. For that reason, there is the possibility that once we work everything through, that we will get a solution that's not actually a real solution. In other words, an extraneous solution. We will explore that once we have solved the problem. For now, let's just continue. We know that cosine squared is the same thing as 1 minus sine squared. Therefore, we can replace cosine squared with 1 minus sine squared. On the left-hand side, we can FOIL everything out. Sine of x times sine of x is sine squared of x. 1 times 1 is equal to 1, and sine of x times 1 is sine of x. But we have two of those when we FOIL them out, so we have 2 times sine of x. Let's get everything to the left-hand side of the equation. We can do this by subtracting 1 and adding sine squared to both sides. That will cancel everything on the right-hand side, and we will be left with 2 sine squared, since we already had 1, and we added 1 more, plus 2 times sine of x, which we already had, and then the 1 and the negative 1 cancel. So we have 2 sine squared plus 2 times sine of x is equal to 0. Both terms have 2 sine of x in common, so we can factor it out. We have 2 sine of x times sine of x plus 1 is equal to 0. By the zero product property, either 2 times the sine of x is equal to 0, or sine of x plus 1 is equal to 0. Solving the left equation, if we divide both sides by 2, we will get that sine of x is equal to 0. Sine of x is equal to 0 twice on one revolution of the circle. The first time is when x is equal to 0, and the second time is when x is equal to pi. These may or may not be solutions. We will want to plug them back into our original equation to see if they hold. There is a possibility that these are extraneous solutions, which only come about because we solved this equation by squaring both sides. That creates the possibility that perhaps one or both of these solutions are not actually solutions. Solving the other equation, if we subtract 1 from both sides, we get that sine of x is equal to negative 1. Sine of x is equal to negative 1 only once on one revolution of the circle. It's when x is equal to 3 pi over 2. Okay, at this point we should check our answers. Once again, since we solved this equation by squaring both sides, there's a possibility that we have introduced extraneous solutions, so we need to check them to make sure that they're correct. Let's check x is equal to 0. If we plug x equals 0 into both sides of the equation, we get sine of 0 plus 1 is equal to cosine of 0. Sine of 0 is equal to 0, and cosine of 0 is equal to 1, so we have 0 plus 1 is equal to 1. We get 1 is equal to 1, which is a true statement. That means that x is equal to 0 is a solution. Let's check our next solution, which is x is equal to pi. We have sine of pi plus 1 is equal to cosine of pi. Sine of pi is equal to 0, and cosine of pi is equal to negative 1. We get 1 is equal to negative 1, which is a false statement. This means that x is equal to pi is not a solution. If you think a little bit more about this, you can see how the other possibility of our original equation would actually be true. If we would have started with negative cosine on the right-hand side, then this would have actually created a true statement. We would have sine of pi plus 1 is equal to negative cosine of pi. In the end, we would end up getting 1 is equal to 1, and pi would be a solution. There is a separate equation when we squared both sides that we would have gotten the exact same results. If we would have started with negative cosine of x, everything would have worked out exactly as it did here, and then pi would have been a solution. But since we started with positive cosine of x and not negative cosine of x, that means that pi is not a solution. Let's check our last answer of 3 pi over 2. We have sine of 3 pi over 2 plus 1 is equal to cosine of 3 pi over 2. Sine of 3 pi over 2 is equal to negative 1, and cosine of 3 pi over 2 is equal to 0. Negative 1 plus 1 is equal to 0, so we get 0 is equal to 0. This is a true statement, meaning that x equals 3 pi over 2 is indeed a solution to our original equation. Let's try one final problem. We are asked to find all solutions to the equation tangent squared of theta minus 3 times the secant of theta is equal to negative 3. Now notice that this problem asks us to find all solutions, not just the solutions on one revolution of the circle. We can solve this by first finding all the solutions on one revolution of the circle, and then finding all of the coterminal angles. You'll see what I mean once we finish the problem. Again, we have two different trig functions. To solve an equation, we will want to convert everything into one single trig function. So we don't want to have tangents and secants, we would like to have all tangents or all secants. We know that we can always convert squared trig functions into other trig functions by using the Pythagorean identities. Specifically, 1 plus tangent squared of theta is equal to secant squared of theta. If we subtract 1 from both sides, we get that tangent squared theta is equal to secant squared theta minus 1. So we can replace tangent squared of theta with secant squared theta minus 1 in our problem. We will get secant squared theta minus 1 minus 3 secant theta is equal to negative 3. Now we have an equation that involves only one type of trig function, just secant. Let's add the 3 to both sides so that we get 0 on the right-hand side. We have secant squared theta minus 3 secant theta plus 2, since negative 1 plus 3 is equal to 2. At this stage, we are ready to factor. We need two numbers that add to our b coefficient of negative 3 and multiply to our c term of positive 2. The two numbers are negative 1 and negative 2. Negative 1 times negative 2 is equal to positive 2, and negative 1 plus negative 2 is equal to negative 3. That means this can be factored as secant of theta minus 1 times secant of theta minus 2. By the zero product property, we know that either secant of theta minus 1 is equal to 0, or secant of theta minus 2 is equal to 0. Solving the left-hand equation, we can add 1 to both sides. We will get that secant of theta is equal to 1. We know that cosine is the reciprocal of secant. The reciprocal of 1 is just 1, so that means that cosine is also equal to 1. Cosine is equal to 1 only one time on one revolution of the circle, which is at theta equals 0. But we need to find all solutions, so any angle that is coterminal with 0 will also be a solution. The way we express this is that theta is equal to 2k pi, where k is equal to any integer. So any multiple of 2 pi will be a solution, either 0, or 2 pi, or 4 pi, or 8 pi, or in general, 2k pi, where k is some integer. Solving the other equation, we can add 2 to both sides. We get that secant of theta is equal to 2. That means that the reciprocal function of cosine is equal to 1/2, which is the reciprocal of 2. Cosine is equal to 1/2 twice on one revolution of the circle. Once in quadrant 1 and another time in quadrant 4. In quadrant 1, cosine of theta is equal to 1/2 at pi over 3. But of course, we need all solutions, so any angle that is coterminal with pi over 3 will also be a solution. We express this by saying that we have pi over 3 plus 2k pi, where k is any integer. so we could have pi over 3 plus any multiple of 2 pi, and that will also be a solution. The angle in quadrant 4 that would also satisfy this equation is 5 pi over 3. 5 pi over 3 is in quadrant 4, and is also related to a point on the unit circle where the x-coordinate is equal to 1/2, so cosine of theta will be 1/2. We also, of course, still need to have plus 2k pi, where k represents some integer, to represent that any angle that is coterminal with 5 pi over 3 will also be a solution. Alright my friends, that finishes this video solving trigonometric equations using the Pythagorean identities.